So I'll talk about active invariant causal prediction, experiment selection through stability. And very recently, I joined the Health AI team at Apple, but this work was done at ETH at the Seminar for Statistics. And this is joint work with a PhD student I co-supervised there, Juan Gamella. So the setting we're interested in here is learning the causal structure from data, or at least parts of the causal structure. So in particular, here we're interested in a setting where we're interested in a particular target variable y of interest, and we want to infer which variables are the causal parents of y in the underlying causal graph. And furthermore, the setting we consider here is where we have data from so-called different environments or domains available. And I'll get into what that means more concretely later in the talk. So even though learning parts of the causal structure is our goal here, let me motivate the methodology more from a prediction point of view and an out of distribution generalization point of view. And that also sheds light on why the methodology is called invariant causal prediction. So in this example, I generate data from the graph shown here on the right. So when we apply our method, of course, the graph is unknown, but I put it here, since it's synthetic, we also know the ground truth in this example. So I generate data from it, and then I compare three different models where we use some subset of the covariates to predict y. And then what I plot in these graphs is I plot the observations y on the y-axis, and then the predictions we obtain for these three different models on the x-axis. So good predictions means that the points will lie very close to the diagonal. So then what are the three models we compare here? So the first one is what we call the causal model, meaning that I just use the causal parents of y to predict y. So in this example, this is x2 and x3. And then the second one in the middle, that is what we call the full model, meaning I just use all available covariates to predict y. And then the last one, which here I call an invariant model for reasons that will become clear later. And here I just use x2 as input. And so what we observe here in this observational environment, so there we don't have any interventions on the nodes in the system, that in fact the full model yields the best predictions, then followed by the causal model, which also does fairly well, and then the invariant model, which in this example shows the worst performance, but I'd say is also not entirely off either. So then what we do next, so we have now data from a different environment available. So I'll call this here the test environment. And in fact, this is generated by intervening on x2 and x4 in this data generating mechanism. So I observe now data from this interventional distribution. And now I just employ the models we trained on the observational data and just see how they perform in this test environment. And so what we observe is that the causal model still performs very similar to the previous settings, so to the training environment, whereas now the full model, which was sort of the best model in terms of predictive accuracy previously, now performs much worse, and one could say it really does not work any longer. And then finally, the invariant model. So again, it performs similarly as before, but still worse than the causal model. So what this example illustrates are the two statements that are shown at the top of the slides, so namely the causal models generalize. And I should say here, the underlying assumption is when we go to these different environments that we don't intervene on y directly. So the underlying assumption is that the data generating mechanism of y always stays the same, but potentially we could intervene on all the other covariates. So in such setting, you can take the causal model to such a new environment and it will continue to yield good predictions. But what we also observe that this is not only true for the causal model, depending on what environments you see, right? So here, what I called an invariant model for this environment also continues to work, even though in this example, it's maybe a bit worse than the causal model, but you could also have settings where a model that is not the causal model actually yields better predictions than the causal model for some particular environment. So depending on what environments you observe, what variations you see, you will generally have multiple models that show this generalization. So now what we observed is actually very well-known properties of causal models, namely that as long as we don't intervene on Y directly, then when we compare this conditional distribution of Y conditioning on the true set of causal parents, that distribution remains invariant across these environments, where these environments are generated by interventions on the remaining variables in the system. And in terms of notation, so S star denotes the causal parents of Y throughout this talk. Now, this has been sort of known for a very long time, but then what this method of invariant causal prediction in that sense exploited was to turn this around in a certain sense and say, well, maybe we can, if we have data from multiple environments, can we find invariant conditional distributions and use that to estimate S star in some way. But as I said before, since given some observed set of environments, there will often be multiple sets of predictor variables or covariates that satisfy this invariance, we still have to work a bit harder. So this is not only true for the causal parents S star. So more generally, so we will call the set of variables that satisfy this invariance, just so if it's an invariant set under some set of observed environments as script E. So then the method goes as follows. So given some observed environments, we will somehow find all the invariant sets. And then to get an estimate for S star, we just return the intersection of all the sets that are invariant given my environments. And like a small disclaimer, so I'm simplifying the terminology and the notation a little bit. I hope this does not cause confusion for those of you who know this work a bit better, but if it does, please ask. Major assumptions here are that you have a cyclic underlying causal system, there are no hidden confounders, and as I already said, no interventions on Y directly. So for instance, this would also mean if you think of the structural equation models, then the structural equation of Y, that the noise in that structural equation has the same distribution across all environments. So then there are sort of different works that sort of worked out how you do this part of the first step, so how you find all invariant sets. So the original paper by Peters and al. Looked at the linear setting and made concrete proposals how you can do this in a linear setting. Then I worked on the nonlinear case, and at Pfister et al. Worked on a sequential time series setting. But all of these approaches are based on statistical hypothesis testing. So for all of these settings, you would design a statistical test where the null hypothesis would correspond to sort of invariance across environments. And then you would test this null hypothesis for all possible subsets of the covariates. And then now a bit more precisely, return the intersections of those sets for which you could not reject the null hypothesis. And so to clarify, this is set up in such a way that this null hypothesis would hold for the true set of causal parents for all possible sets of environments. But then for some environments, this may also hold for other sets S. And so one nice property of this method is that it has the following guarantee. So you can show that the estimate you get S hat is a subset of the true causal parent S star with high probability. And this comes from the fact that so we test this null hypothesis for all possible subsets of the predictors. So at some point we will test the true set of causal parents. And then since we know that the null hypothesis is true for those, we know that we don't reject with probability larger than 1 minus alpha where alpha would be the significance level of the associated statistical test you use here. So this essentially means we have a guarantee that our estimate does not give false positives, it's high probability. And in some applications, this is really a feature because you can say, okay, the result I get is in that sense, so we have high confidence edges in some sense that we estimate here. But on the other hand, it also comes at a cost of lack of power, let's say. So when you run this, given some set of observed environments, you also often may end up with the empty set. So then, of course, the statement is still true, but the output in that sense is not very informative. So then it should not be interpreted as saying, okay, Y does not have any parents, but it may as well mean, well, I don't have sort of enough variety in my environments to detect the causal parents here. So in that sense, you would also say it's a conservative method in the sense that it sort of, depending on the environments, the output may be uninformative, but if you do get a non-empty set, you can be pretty confident that this is indeed a causal parent of Y. Mm-hmm.
Are there any results that give you non-trivial power for this type of? Are there any results that give you non-trivial power for this?
I think not directly, but what I will talk about is this active setting where you can intervene in the system. And that essentially sort of then shows you how sort of quickly you gain power or not. Yeah.
Since there's could be many different subsets to search over, this would be like a multiple.
Yes, so in that sense, it's an expensive method because you need to sort of, given your available covariates, you need to check all possible subsets.
That so would also affect your statistical kind of.
So the thing here is it only matters what you do when you test the true causal parents. So the testing errors at the other sets would not affect this guarantee. So that's why if you just run this on sort of once, you don't need to adjust for multiple testing errors. In the setting I'll talk about, you actually do have to adjust because we'll run the method multiple times. Anything else at this point? Okay. So what I want to talk a bit more in this talk is this aspect of the different environments. And let me start by giving you a sense of also the real data sets that this has been used on. So this has been employed on a gene perturbation experiment for yeast, where as environments you take wild type versus gene deletions. Then in the context of nonlinear ICP, this has been employed on a data set from the UN where the target variable of interest, Y, is the total fertility rate of a country. In there's environments, we could use the different continents. And then finally, sort of also one fairly classic application of causal structure learning algorithm is this data set from Sachs et al., which is about protein signaling network estimation, which is then based on flow cytometry data. And there, the different environments are different experimental conditions that you can use. And I would say when you apply this in practice, sort of the results are somewhat mixed in the sense that sometimes you do get like non-empty sets. And then again, we have sort of this confidence that, of course, if our assumptions are satisfied, that these are now, in fact, like causal parents. But often you also get the empty set as a result. So hence, we wanted to understand a bit better sort of what is, say, the conditions on these environments that maybe give you more power. And then concretely, if we say are in a setting where we can directly intervene in the system, how should we sort of perform interventions to improve the power of this method? And so from the beginning, it was clear that heterogeneity plays a key role and that sort of heterogeneity is good. But so we were then a bit more concretely interested in sort of what kind of heterogeneity helps. So now for this purpose, we focus on this setting, the active causal learning. So we want to learn the causal structure, but we also assume that we are able to actively perform interventions on the covariates in the system. So we would always have these rounds where we would choose an intervention target. Then we can, say, perform the experiment, collect the data from it, and then run our causal discovery algorithm on this newly created environment and the ones that were previously available. And in this work, we focus on ICP as this causal discovery algorithm. So let us look at an example of how this would go. So here again, I show the underlying graph on the left, but again, this is unknown when we run the method. And then I plot here just these single predictors against Y, but again, the method internally would have to consider all possible subsets. So when we start out with just one environment, so in practice, you would not run ICP with just one environment, but in principle you could, and you would find, well, sort of by definition, everything is invariant. So when you take the intersection at this point, of course, it's still empty. But now let's start to perform interventions and say, since the graph is unknown, at this point, we don't have a better idea than just performing interventions at random. So say the first intervention, you perform X on X4. What happens is that all sets that contain X4 sort of drop out, so are no longer invariant. But when we look at the remaining invariant sets and check what is our ICP estimate, it's still empty. Then we continue to collect data. This time we intervene on X3. And this time, in fact, this did not help at all. So the invariant sets are exactly the same as in the previous iteration. Then we continue intervening on X1. So now all the sets that contained X1 drop out, so they're no longer invariant. But unfortunately, we're still unlucky, and the intersection still yields an empty intersection as the final estimate. So then the last step, we finally intervene on X0, and now this time we end up with an estimate S hat being equal to X0, and this corresponds then to also to S star. But now, of course, the natural question is whether we actually needed all these environments to arrive at that final estimate, or whether with different environments, this would have been easier, or so if we would have achieved the true estimate faster.
So within this ICP, you do the second step. And I mean, wouldn't you now also have this issue that it's inference after selection, and you do selection and then the p-values on top of the selected subs is not just a number, it's also that you adaptively select it?
It's a question I would have to think about that further. Okay, but let's see what happens if we chose a different subset of environments. We first start out again with this one, but then this time we intervene on X0 again. So with those two environments, we now directly arrive at the true so the correct estimate, even though the invariant sets we have now here are with much more than in the previous example. But for our ICP estimate, in that sense, that does not matter. So in that sense, some environments are more informative than others. Here now in the context of running ICP and getting a good estimate for S star. So then in this scenario where we do have the option to intervene on covariates, we ask ourselves, okay, how do we select informative experiments? Is there any sort of signal we can exploit to not do this at random, but do this potentially in a bit smarter way? So then the question is, okay, what is an informative intervention? So since our downstream goal is to eventually run ICP and estimate the parent, we say that an informative intervention is the one after which the largest number of parents appear in the estimate. So now in this context, this is our definition for an informative intervention. So then something one can show quite easily is if you directly intervene on a parent, then it appears on all invariant sets. And here I should point out, and this is where we have to be a bit more precise. So this is a sort of population statement in the sense that this assumes sort of no testing errors. So of course, in practice, when you run this on a small sample size, you might have testing errors that then mean that this does not happen. In the population setting, of course, it would mean since we have this result, I just need to intervene on everything once and I'm done, because then I have intervened on all the parents. and then the intersection will then give me the parents exactly. But then in finite samples, unfortunately, it's not that easy. When you have small sample sizes and potentially also not very strong interventions, then due to the statistical testing that underlies it, you need often many more interventions than just intervening on everything once. So now, due to sort of this observation, we treat interventions as parents as maximally informative. But here I should also say there's a caveat that for certain graph structures, it would actually be better to, say, intervene on answer shifts that are further up the graph. And if I do that, I might actually, as a result of that one intervention, have multiple parents that appear in my ICP estimate. So in that sense, directly intervening on parents is not always optimal, but it will depend on the graph structure. And since the graph structure is unknown, it is hard to detect these cases in practice. So now the key idea here is that we can actually look at how these invariant sets sort of behave as we add interventions. And they have sort of properties that we can exploit for selecting experiments. So one thing is that parents appear on at least half of all invariant sets at any stage. So no matter what the environments are, and no matter whether I intervened on a parent or not. So we can always check sort of these ratios. So how often a certain covariate appears on these invariant sets. And hence we would not intervene on variables that appear less often, because we know that these are not parents. And our goal is to intervene on parents, even though, of course, we don't know which covariates are the parents. And then another simple thing you can exploit is that look at the marginal distribution of Y. And if that is invariant under a set of environments, then you know that none of the interventions in that set of environments were performed upstream of the response. So from that, we derive the so-called empty set strategy, which says that if after an intervention, the marginal distribution of Y is invariant, then we would discard the intervention target from future interventions. So we would not intervene on that variable again. And so in practice for this, we would assume we have some observational environment where we know there are no interventions, and then we can always contrast that environment and then take the latest intervention. So then evaluate this based on these two environments. And also here, so this empty set strategy only makes sense in a finite sample setting due to what I said previously, that in the population setting, we don't need to intervene on any variable twice anyways, because intervening on everything once is sufficient. So this empty set strategy is really something that is only useful in a finite sample context, but we will see that there it's actually fairly effective. Mm-hmm. I guess I don't have a very good intuition for it. I mean, it's not a difficult proof, but I think there's, yeah, I don't have sort of very good intuition. Also, what I should say, so these results, so this property about the parents, it's fairly general. So in fact, it's based on the graphical notion. So we don't need parametric assumptions at this point, even though the results I will show later on are based on a linear setting. And also sort of one catch to this. So this is true for parents, but it's also true for answers more generally. So unfortunately, this does not give us like as much signal as we first hoped. But we can deduct from it that variables that have a ratio of or like that appear less than half, that those are not parents or not answers more generally. Yes. So then we have these different strategies. So the first two I just mentioned, and then the last one is also sort of a natural thing you might consider in this setting, that you say, oh, I try to estimate the Markov blanket, and I pick intervention targets from within the Markov blanket. And then so we have these three different strategies, which would in general just narrow down the possible intervention targets, so the possible covariates we can intervene on. And then we can, of course, also combine these, and which would further shrink the pool of possible intervention targets. So when we speak of a policy, it would be some combination of these three sort of base strategies. So then these are some experimental results. So in each of these plots, on the y-axis, we show the average car similarity. And on the x-axis, we show the intervention numbers, also the number of environments. And then we do this for different sample sizes. So just 10 observations per intervention or environment, then 100 and 1000. And so the different lines of all the different combinations of the strategy I presented, and then the solid red line is just the random strategy. So this would be the the one we would like to beat. And here we observe, like, for small sample sizes, that one is so maybe surprisingly hard to beat, because these strategies I introduced, right, they all rely on estimating some quantity. With small sample sizes, you will make errors there, which the random strategy, of course, is not subject to. But now, even for these few observations per interventions, we see that this empty set strategy is actually quite effective at obtaining a large average car similarity fairly quickly. And also for the other sample sizes, it's, I'd say, the one that's of most robust across a large number of settings. What was initially a little bit surprising to us is that exploiting the Markov blanket does not work better. And that is really due to the estimation errors we get. So if we focus here, so for instance, in the right plot, in the first number of interventions, so all the strategy or policies that exploit the Markov blanket, so initially have the best performance. And that comes because the estimate of the Markov blanket will typically contain some parents, but not necessarily all of them. So then we quickly intervene on these parents and they end up in our estimate. So we have those, but then we also miss some in the estimate and we will never intervene on these. And then as a result, they will never end up in our final estimate. So that's why, unfortunately, relying on the Markov blanket is, in that sense, good if you have only a small budget for interventions. Then you could say, okay, if you know beforehand you can just perform very few interventions, then it's maybe something you would want to do. But if you can perform a larger number of interventions, these estimation errors you will make there will hurt you down the road. And some details I did not mention. So this is typically P is number of variables. It's 11 or 12 in this example. So it's still a fairly small problem because you have to perform all these tests for the different subsets. And this is average, I think, over 300 different structural equation models. Then finally, one comparison with the competing methods. So it's the Bayesian approach ABCD. And maybe at the outset, I should say, so these methods are not perfectly comparable because they have different strengths and weaknesses in different settings. So for instance, ABCD would require a large observational sample, but then the following samples, so the interventional ones, could be quite small. So it could be as small as 1 observation per experiment. Whereas for this active version of ICP, we don't need a large observational sample, but we need say a reasonable number of data points per experiment. So here we try to establish a sensible middle ground for these two methods, but in that sense, in different settings, you would see somewhat different behavior. So what we then plot here, so the left plot is the same as you saw on the previous slide. So average car similarity as a function of the intervention number. And then on the right-hand side, we plot the family-wise error rate, which is here defined as the empirical probability that the estimate you get, so the S hat is not a subset of S star. So starting on the left, what we see is that, so in terms of power, ABCD starts out higher. So with just very few interventions, it gives us a higher car similarity, but then it somewhat plateaus towards the end and does not approach 1 as we perform more interventions. And for AICP, in contrast, you see at the beginning, we start out by 0. So due to this conservativeness of the construction of the estimate, but then the power increases as we add these environments. And finally, we also we reach a number very close to 1. And what we see on the right-hand side, when you look at the family-wise error rate, that indeed for AICP, so this is controlled as it should be by construction, but for ABCD, you see that so it's not, so you do get false positives. And it does not get rid of these false positives as you add intervention. So this is also then why we don't reach the perfect Jacquard similarity on the left. So depending on the context of what is the cost in your setting for false positives versus false negatives, you may want to choose one method over the other. So to conclude, so what we saw, like causal models are invariant and generalize, and invariant models with respect to some set of observed environments are potentially causal. And heterogeneity plays a key role in the performance of invariant causal predictions and the power you get. And here some informatives, some environments are more informative than others. And in AICP, we collect these informative new environments by observing which models are invariant given the current environments and how that changes. And this may help to find the causal model more quickly, also depending on sample size and intervention strengths. So seeing like, yeah, what power you have and how much the setting challenges the statistical testing you do underneath. So that's also maybe a comment about the different performance of these methods. So for this ratio statistics, really we sort of use all the test results. So errors in those individual tests will sort of bias that statistic, and hence that hurts sort of the selection process. Similarly, this anti-set strategy we formulated also relies on the test result and may then also make mistakes. There may be one point of discussion at the end. So ICP, when you run it, it does not require knowledge of the intervention locations. So that on the one hand, it makes it robust to off-target effects, as long as they don't affect Y itself. And in this framework, you could also say you combine existing environments with where the intervention targets are unknown with more of these actively collected ones in this framework. But on the other hand, we also discard information we now have for these actively collected environments, right? That we do know where we intervened. And this is not really exploited in the underlying methods. So potentially, yeah, there's still room to improve this procedure by building in this knowledge more explicitly. And with that, I'd like to thank you for your attention. And yeah, happy to take any more questions if there are any.
How would you use the active ICP method for learning the entire graph? So if you're not just interested in the parents, I guess there are some differences to the non-active setting where you just do proportional, but now it would probably inform the intervention selection as well, right?
It's a good question. I mean, right naively, what you could always do is the same as for the non-active one, that you did do this for every node. I mean, I guess my intuition is you cannot do so much more because right then the target always changes, right? So you always have a different regression problem you would have to consider, and hence it does not seem like you could benefit so much from the results you already collected in the active setting. I mean, you can of course sort of leverage the collected data, but you would have to rerun the models. So, and then how the collected data, I mean, it's probably something you should exploit, but in that sense, not really collected for that other target. So it seems like, yeah, you could probably gain something, but I would imagine for some parts of the graph also it may not help you much. Especially for very large graphs, right? So when you try to do something really local, sort of around Y, so if you have very large graphs, yeah, it might not help you so much, but it will also depend a lot on the exact graph structure.
Yeah, thanks for the nice talk. I guess I have two questions. They're quick. The first one was about in the regular ICP, you have this kind of statistical guarantee that you'll include the right set of parents with high probability, and you can have this confidence interval. So can you comment on how that, whether you have anything like that in this active setting?
So the strategies sort of we formulate are just for the environment collection, and then you just take the environment and run ICP on top. So all of that carries over.
And then another quick question, I guess, was about, you mentioned the application to this UN health data where your environments were different continents. And can you comment on, so most of the examples are in settings where there's an actual intervention, and that's one in which I guess you're assuming that there's it's kind of like an intervention because it's exogenous. So is there any advice about how that should work, I guess, in these observational settings?
So I think there's sort of not an immediate connection, but I think in some settings, at least, sort of these considerations and these sort of small results we derived here could maybe sort of inform the choice how you define or form the environments in more observational settings, that you sort of, try to reason a bit more, okay, is this something that acts upstream of these other covariates? So maybe when you have some background knowledge, it might sort of inform how exactly you define the environments. But yeah, how much background knowledge you have really depends a lot on the application. I mean, another sort of related point to this is, so from the results, right, we saw, okay, we want to intervene on parents because then, at least in the population setting, it means we don't have that parent in our estimate. But in the finite sample setting, often that does not happen. And we actually have to intervene multiple times until we finally have enough power that this happens. And sometimes it's actually quite effective to intervene on a child because it will then often rule out a number of sets that were previously still invariant. And I think that is, I mean, it's more of an empirical observation, but I think in this sort of UN settings, right, we define these environment variables and you somehow need them to be upstream in the graph to sort of make the testing problem to work. But now I think, yeah, maybe one can also bring in this additional observation that sometimes if you intervene on a child, it will help in terms of ruling out invariant sets. And it will in turn help you estimate when you take the intersection of things. But then how exactly you would do that, I think that is open.
Thank you.
Can you, so one part that's not clicking yet in my head is this result that you had with the Markov blankets, right? And so to me, it seems that, look, if I have a ton of observational data, then surely I should be using that to somehow get like a rough structure of the graph and then not worry about things that are far away. And that's not quite a Markov blanket. So part of me thinks is that, look, if you're getting estimation errors in your Markov blanket, be more conservative about what you consider to be the Markov blanket, and then go, what's going on there?
So I think, yes, so an important sort of point is, are you in a scenario where you have a lot of observational data, or are you in a scenario where maybe sort of all of these different environments are of a small size? Because then, right, you would have to estimate the Markov blanket from a small sample, and then you have these errors. And I think you're right that the larger n, the better our estimate should get. But even so, like this, the largest we show here is n is 1,000. Even there, so for many graphs, we still observe this behavior that, yes, initially it helps because it will directly intervene on the parents we have included. But there's still many cases where we leave them out. And I mean, we try to play this with sort of I mean, it's estimated by the lassos. We played with the regularization parameter, but it was not sort of as straightforward of just saying like, okay, regularize less, and then we will always have an overestimate. So unfortunately, we could not sort of get it to work better. And I think it's a bit in line with also the observation that sort of estimating the PDAC from observational data empirically for say medium or small sample sizes, unfortunately does not work as reliable as one often would hope it to work. So I feel it's a bit of a similar sort of thing going on here.